other chats that for business reasons.
Justin, how are you doing, Justin?
Sorry.
What do you want to see, Megan?
Sorry, you're such a bad I'd say I'm bad.
Just like if you want to go through the code to read a problem and set it up.
Pick one for me?
Okay. Oh, thank you.
3 or 4? 4?
Just looks like they did.
So the exam with 20 true false questions, that one?
Yeah.
Okay. So they tell you the conditional probability that a student knows the answer to a question given that they answered it correctly is whatever it happens to be. So the information, or the conditional that you're given is knows the answer given a correct answer, right? That's what they tell you that in that last line of the problem, right? It says the conditional probability that they know the answer given that they answered it correctly is what that happens. So the reason I wrote this down first is because that was just given to me what I had, correct? Okay. So if I work with this, how can I rewrite the conditional?
Probably K intersects C over probabilities.
Okay. All right, so at this point I need to start getting some other information out of the problem to help me figure out how to get stuff on this left-hand side, because we need to figure out, what is it? Oh, we're trying to figure out what the n is, right? All right. So on the top, we know that we can basically reverse the conditional as what? Probability of they know the answer, probability that they answer correctly given that they know the answer. All right, so let's look at this part here. Let's just look at the last part. It says the probability that they answer correctly given that they know the answer. Is there anything in the problem that tells you what that has to be? Yeah. Given that you know it, what is the probability that you answer it correctly? 1, right? So I know that this part is 1. So we just have the probability that you know the answer over the probability that you answered it correctly is 0.824. All right, still not where we need to be, but at least a little bit closer, right? We simplified it a little bit. We got rid of that conditional in there. All right. In this problem, it says that there's 20 true-false questions, and the student knows n of them. So for a particular question, for any particular question, if you select a question at random, if they know n of the answers out of 20, what's the probability that they know the answer? Maybe it has to be n over 20, doesn't it? So, yet another step closer, right? Notice I'm just trying to go a step at a time in these to try to figure out where to plug individual pieces in. The reason I started with the conditional is because I actually have a formula for the conditional where I could break it apart. And we've already talked about when we're doing these particular problems that involve Bayes' theorem, we're talking about reversing the conditional around, right? So there's another reason why I did that one to start with. All right, so now it's this denominator. And when you're looking at the denominator using Bayes' formula, Bayes' theorem, typically we want to break up the problem, or excuse me, break up the denominator into pieces, right? In most of the problems that you did in this particular handout, it involved breaking up the set into disjoint pieces. Well, in this particular case, how can you get an answer correct? What are your two possibilities for getting an answer correct? Yeah, either you know it or you don't, right? You knew it and you answered it correctly, or you didn't know it and you answered it correctly, correct? So, writing it in formula terms, this would be the probability that you got it, you knew it and you got it correct, or you didn't know it and you got it correct. And this is typical in these Bayesian problems where I'm going to break up this denominator where it says the probability of a whole set. I'm going to try to break up that denominator into pieces that are disjoint and make up the whole set. In this case, I know it or didn't are disjoint by default because they're complements of each other. So then from this part, I can do this with, I can write it out as conditionals. Probability that you knew it, probability that you answered it correctly, given that you know it, probability you didn't know it, probability that you answered it correctly, given that you didn't know it. Well, we already calculated this first part in the numerator, didn't we? It's exactly what we calculated in the numerator. So this will be n over 20 times a 1. Well, if the probability that you knew it is n over 20, what's the probability that you didn't know it? It has to be 20 over minus n over 20, right? Because the rest of them you didn't know. And then what happens if the student doesn't know the answer? What do? Guess. You're doing a true-false question, and you're just going to guess the answer with the probability you get it right. 1/2, right? So this now gives you an equation to solve for n, and what's probably just as easy as anything is start plugging in the numbers in our answer. See if you can solve this for n, but probably just as easy just to type in a calculator. As a matter of fact, if you use your previous answer button, you can change it and then go back and grab the previous entry. You can change things pretty quickly, right? You answer divided by 20 over, just put it in that way, and just retype the answer. Plug it in pretty quickly. At this point, it's just a matter of figuring out what the n is. I don't know what it is. Between 1 and 20, that's probably between 0 and 20. Yeah. Yeah, Megan.
Okay, can you just explain how you know which part is the given and which part is not? Like how you write the probability of...
At the very beginning?
Yeah.
Or, okay. So in this particular case, it says given, right? So that's how I know that's the second part. But if it explicitly tells me that it's given, then it says the probability that the student answers correctly, probability that they knew the answer given that they answered correctly. So since it said given that they answered correctly, I know that's the part that goes after the given. And then the other ones, I knew that I wanted to switch the order because I was given to it in terms of given that they answered correctly. Other questions? Yeah, Sam. 3.21. You have to remind me what it is. I forgot to bring the sheet with me.
A doctor
Studying
the relationship between blood pressure and heart apparatus.
Oh, okay. I know what it was. All right, what pieces of information do you know?
14% have high blood pressure.
Okay, so the probability of high blood pressure is 0.14. Probability of low blood pressure is 0.22. These two together tell us what the probability of normal blood pressure is, don't they? Doesn't it? 0. What? 64? Okay. Good. Because I know that a person has to have high blood pressure, low blood pressure, or normal blood pressure. Right? Now this one's a little bit more, probability that you have an irregular heartbeat is 0.15. This tells us the probability of a regular heartbeat is 0.85. Because I know that irregular and regular are complements of each other. All right, so this one's a little bit more with the reading of which one's the given and which one's not. This one says, of those with an irregular heartbeat, 1/3 have high blood pressure. So what part of that is the given? Yeah, the given I, right? So of those with irregular heartbeat. So that's the given part. Probably they have high blood pressure is 1/3. Of those with a normal blood pressure, so that's the given, right? 1/8 have an irregular heartbeat. Now we're trying to get regular and low blood pressure, right? All right, so to get to that point, I think there's not a lot that I can do with these that I haven't already done, right? I took these two to find this third one. I took this one to find this one, right? I'm pretty much exhausted what I can do with those. I'm going to play with the conditional probabilities to see what we can get from there. All right, how can I rewrite this conditional probability? I know the probability of H given I is 1/3, right? And we know the probability of I is 0.15, right? This part right here is 0.15. So we can get this, we can get to the probability of H intersect I is 0.05, right? I'm just trying to get more numbers. I'm not really having a plan here. I'm just trying to use the formulas, use the given information, see what else I can get out. I'm really not having a creative thought here at all. Okay? I just have a formula, plug it in, see what I can get. I'll worry about creativity. Once I exhaust all of that, then I'll worry about creativity. Okay? Same thing with the second one. How can I rewrite the probability of I given N?
Probability of I intersect N over the probability of N.
Good. That has to equal 1/8. I know probability of N was what? 0.64. That was one of the other pieces that we computed previously, right? So this gets us to that the probability of I intersect N is 0.08. And at this point, I think we've exhausted everything that we can do that involves just using formulas and the given information. All right? Now we have to be a little creative. So let's look at the two things that we just figured out. Well, we figured out how H and I intersect and how N and I intersect. Well, H was high blood pressure, N was normal blood pressure. What's the only other case? Low, right? Now think about what I has to be made up of. Well, it has to be made up of people with high, low, or normal blood pressure. It's the only possibilities, right? So we know that this is where the creativity comes in. We know that the I is made up of, oops, you don't write it that way. High blood pressure people, normal blood pressure people, and low blood pressure people. Right? And do we know probabilities for 3 of those things?
Yes.
Yeah, right? We were given this one, and we computed these two. And we also know that these are all disjoint, right? So I know that the probability of I is the same as the probability of I intersect H, I intersect N, and, oops, these are pluses. And I intersect L. This was 0.15. This one was what? 0.05? This was 0.08. So what does I intersect L have to be? 0.02. So again, that was using a little bit of creativity, right? It wasn't a formula that we were given. However, this idea of taking a bigger set and chopping it into disjoint pieces is a technique that we have, right? We saw it in the Bayesian stuff several times, right? You rewrite it in that denominator, you're typically having to break it up into pieces. So it's the same idea here. Finally now, we're looking for the probability of R intersect L, right? Well, again, if you're a person with low blood pressure, either you have an irregular heartbeat or a regular one, right? What percentage have a low blood pressure? The percentage overall of low blood pressure is 0.22, right? How much of that have we already accounted for? 0.02, so we need to subtract, right? So this will be 0.22 minus 0.02 to give us 0.2. And again, that's because the low blood pressure people are made up of irregular heartbeats and regular heartbeats. So what's left over had to be the regular heartbeat. So again, when I'm attacking these problems, notice the first thing I did was just basically spew out information just based on the formulas and what I was given. I didn't try to be creative. I didn't even look at what I was being asked to compute, right? I'm just trying to get as much information onto the page as I can and then figure out how to piece it together. As soon as I did that, I saw that we had that overlap between the I, right? H intersect I, N intersect I. I've got two pieces that make up I, and I wanted to know the third. So that was when I had that little bit of creativity so I could figure out the third. Increase. Have I made a table for this? Yeah. How did you make a table? Yeah.
I can tell you, but it wouldn't come out. I did that too, and it made it easier.
Grace tried to explain something to me.
It was
I'll
like,
show you.
Irregular, high, low, normal, and then you were given this, and this, and then that would tell you that you needed to solve for this and this to get this and then get that. So like I think this was like point.
I mean, if it helps you organize the information, that's perfectly fine.
That's what I mean, like, and it's less creativity and more like telling you like where you need to go, I guess.
So
Bottom right corner has equal one.
I mean, you can do this with your conditional problem. Okay, so this. Oh, what did you have? This was 0.14. This was 0.22. So you get this one is 0.64. This is 0.15. So you get 0.18 or 0.85. So that has to be 1 over there. So to get these. This one? Yeah, that's what we did, isn't it?
Yeah.
Yeah. So you know that you're given, I mean, if it helps you organize the information, great. I'm not sure to get away from having to use the formula, though. Just trying to organize the things? Is that what you were doing?
It's just, you were talking about having to be like creative and just writing down random things, but I found that I had a lot of trouble not knowing where to start. And I just thought that helped me know where to start.
So how did you know to get to here?
I just looked at the givens and like what I needed to find, and it just like basically built me a roadmap of how I was going to get to my goals.
Okay. That's fine. I'm okay with it. There's more than one way to think about it. Absolutely. Absolutely. Yeah. I mean, you still went back to that formula, though, yes? Yeah. So you're thinking. guessing. You're thinking of this as being H intersect I here. Okay, cool. So you were given the H given I part, and you know you need to fill in that piece of your table. So you use the information to fill in that piece of the table. Gotcha. Yeah, that's fine. Yep. Yeah, there's no, the way that I think about the problems isn't necessarily the right way to think about the problems. It's the way I think about the problem. But again, if you don't really know where to get started, just start, well, playing around with things. That's all I did, right? I didn't do anything. Like I said, I didn't get creative until this part. You'd still have to, part of the creativity here would be, again, okay, I know I need to fill in this spot because I was given H given I. I know I need to fill in this spot because I was given I given N. And then once you fill in those two pieces, then you can fill in this part here. So there's still a little bit of creativity involved. This might help visualize it better for some people. Visual is not my thing. So if there's a way to visualize it, I'm more than happy to listen to suggestions. Because like I said, visualizing my head is symbols because I'm an algebraist. So I don't see visual pictures very well. So if this helps visualize and organize things, please do it. Talk to Grace. Grace has got a lot of customers. All right. But again, the idea behind these types of things, the big idea, whether you visualize it this way, whether you another thing that I like to think about it is just, okay, well, if you've got your whole set I got to break it. I have it in 3 pieces, right? You had the high, the low, and the normal, and I figured out 2 of them. You have 3 disjoint chunks of it, right? So I need to figure out 2 of the 3. Again, the big idea behind this and the stuff that was in that Bayes' theorem handout is being able to take a bigger set and slice it into pieces. However you best visualize that is the way you should do it. But that is the crux of the matter, is to take that big set and cut it into smaller disjoint pieces. It's the whole point. All right. Let's talk some more about probability distribution, or probability mass functions, probability distributions. So, remember last time we said that the probability mass function is what we're using to compute probabilities for particular items in the sample space. Right at the end of class, we talked about random variable. The random variable idea, again, is to take a qualitative outcome of an experiment and quantify it. That's all random variable means. One of the problems that you had in the homework was to figure out the probability that the first 3 rolled was on a particular roll. Well, rolling the first 3 is not a quantity, right? Rolling the first 3 is an outcome to the experiment, right? You're going to roll and roll and roll and roll and roll until you see a 3, right? So what the random variable did is took that outcome of when do you roll the first 3 and quantified as the roll number. That's why they use the capital X in that case, was because you're quantifying what the qualitative variable is. The qualitative variable is when do you roll the first 3, right? Rolling the first 3. That's what you're looking for. That's the outcome. You're just trying to count the number of times it does that. That's the function, right? That's the only difference that we really mean by random variable. The random variable is quantifying the experiment. That's all the random variable is. What we're going to be doing with these probability mass functions now, and probability density function later, is using that quantification to calculate probabilities. Okay. So there's that step that goes from qualitative variable to quantitative variable, and then doing the probability analysis based on the quantitative variable. So basically, the random variable part is just changing words to numbers. That's the big part. All right. So one of the things that we mentioned last time was that when you do the probability mass function, when you do the sum over all possibilities, you have to get to what? When you do the sum of all your probability mass function over all your possibilities, what do you have to get? 1, right? So this is number 2.13 in your text, or 2.1-13 in your text, sorry. We've got a probability mass function of 1 over x plus 1, 1 over x plus 2, for x equals 0, 1, 2, and so on. This problem asks you for the probability that x is greater than or equal to 4, given that x is greater than or equal to 1. I want to calculate this conditional probability. Well, your homework was all over conditional probability, right? How would I rewrite this using your conditional probability formula? Not worrying about summations or anything yet. How would I rewrite this just using your conditional formula? Okay. Good. Okay, we do the probability of the intersection over the probability of the given, right? Right? How we do that? So let's see if we can simplify this a little bit before we go through the probabilities. Probability of x is greater than or equal to 4 and x is greater than or equal to 1. Can I simplify that statement a little bit? Yes?
Probability that x is greater than or equal to 4.
Why?
Because if it's greater than or equal to 1, that's already going to be included if it's greater than 4.
Good. Yeah, probability of being x is greater than or equal to 4 is a subset of being greater than or equal to 1, right? So if it's greater than or equal to 4 and greater than or equal to 1 at the same time, it's the same as being greater than or equal to 4. I don't have to worry about the greater than or equal to 1 part. All right. So now using the fact that I've got a probability mass function, I want to do a summation to figure out these probabilities, right? It's 4 or greater. So using the PMF, this has to be the sum from x equals 4 to infinity of 1 over x plus 1 times x plus 2 over the sum from x equals 1 to infinity of 1 over x plus 1 times x plus 2. We can do this directly or we can be clever. I think I'm going to prefer to be clever than direct on this particular one, but if I were going to be direct, I would need to rewrite this series using a technique so that I can get some subtraction. Remember what the technique is? You use it in Calc 2 to do some integration problems.
Partial fraction.
Yeah, so it won't be by parts I'm not doing an integral here, but that's one of the techniques we use. But yeah, partial fraction decomposition to split this into 2 pieces, right? And then you would do a sequence of partial sums.
Is that telescope?
Yeah, it's telescoping. Yep, sure is. Yeah, each of them would be telescoping. It turns out that if you wanted to do this directly, it turns out that 1 over x plus 1 times x plus 2 is 1 over x plus 1 minus 1 over x plus 2. So your top will end up being, I mean, if you do it this way, your top will end up being a fifth and your bottom will be in a half. Because it'll end up telescoping, your middle terms will cancel out. So this would be your direct method, using partial fraction decomposition to get to this point. What if I don't want to be that brute force and have to figure out what the partial fraction decomposition is? What if instead I wanted to be clever? What would be the clever way to do this so that I could just do it? Yeah.
Take out the first 3 terms of the x equals 1, so that way you have the series start at x equals 4 of 1. Cancel.
I don't know if I can cancel those, it'll be sums, right? Instead of products.
Summation from 1 to 3. And that 1.
Let me ask it this way. Can I turn the infinite sum into a finite sum? Yes.
Yeah.
Okay, so I could do complements, right? I know if I add this up from 0 to infinity, what do I have to get? When you take the sum of the PMF over the entire sample space, what do you have to get? 1, right? So I can do this with complements. This would be the equal to 1 minus the sum from x equals what to what? What would be the complement from 4 or greater? Where does it start again? 0 to 3, right? The x started at 0. And then how can I rewrite the denominator?
1 minus sum from 0 to
0 to, actually it would be 0 to 0, right? It would just be that one term, right? So notice that I can, instead of having to worry about partial fraction decomposition and then taking a limit, I can just use the complement and do finite sums and then just plug them in, right? Because this bottom one literally is just plug in 0, isn't it? So I get a half on bottom, right? I get 1 over 1 times 2. So on bottom we get a half. On top we would have 1 minus a half plus, what do you get when you plug in 1? A sixth. When you plug in 2, you get a 12th. And when you plug in 3, you get a 20th. One times 2, 2 times 3, 3 times 4, 4 times 5. And again, I didn't have to do anything with partial fraction decomposition, figuring out that it was a telescoping sum, taking a limit, those kind of things. I could just do it with the finite sums. Either way. I believe that simplifies to 2/5. I did the part of my head correctly, it simplifies to 2/5. Yes.
So then, get the answer from that formula,
Even though I changed what?
the balance.
What I did was I wrote it as a complement. So instead of being 4 or greater, I did 3 or less and did 1 minus that. So I just did the complement. Yep. Is this okay? Yeah, you get 2/5. Yeah. Yep, I agree. You can do it either way again. It's just I think this way you wouldn't have to necessarily worry about the telescoping sum. You can write it as a complement. All right. Yeah.
Why did we choose forward?
What? Oh, that was just what the problem asked.
Oh, that was
Yeah,
in the problem.
that was in the problem. Yeah. Yep.
Okay.
Yep.
I was like, this right there.
All right. So let's go on to the next section and talk about mathematical expectation. And to do this, let's just look at, this is problem 2.23 in your book on page 66. It says that in a particular lottery, 3 million tickets are sold for 50 cents apiece. There are 12,000 $25 prizes. There are 4 $10,000 prize. Excuse me. Yeah, 4 $10,000 prizes. There is one $50,000 prize. And there's one $200,000 prize. You buy one ticket. What is your expected value of the game? So what expected value does is it gives you a way to calculate, on average, what should happen over the long run. Obviously, your outcome for the game, if you buy one ticket, is either you're going to lose 50 cents, you pay 50 cents to play, right? So you're either going to lose 50 cents, or you're going to gain these amounts minus 50 cents. Right? Those are the only 5 possibilities, right? You're either going to lose or you're going to win one of these 4. Okay? Now, what the expected value isn't going to say, what are you going to do on this particular game? What it says is that if you were to play the game over and 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 over, what would you expect to win or lose on average per game? Okay? So what mathematical expectation really is the weighted average. So this is how basically casinos work. You can go to the casino and win money, but more often than not, you're going to go to the casino and lose money. Somebody has to pay the lifeboat. It's typically me when I go to the casino, but somebody has to pay the lifeboat. Okay? Okay? So, but of course, you might go and you might win. That just means a bunch of other people are losing. Okay? But when they calculate the different odds in the game, they're always going to put the odds in their favor to make sure that over the long run, because you think about how many people go into casinos every day, every week, every year, over the long run, they're going to make money. Because over the long run, the expected value will be in their favor and not in the player's favor. All right, so let's see how this works. We'll worry about the 50 cents each at the end. Let's just think about your probability for winning on one ticket. Okay? So there's 3 million tickets sold. What's the probability that you win one of the $25 prizes? The 12,000 divided by the 3 million would be your probability that you win one of the $25 prizes, right? So what this fraction here gives you is a percentage of the time that you'll win $25. So if I want to do a weighted average of these things, I will win $25 this percentage of the time, right? So I would multiply this by the 25. What's your probability that you win one of the $10,000 prizes? The 4 out of the 3 million, right? That's your probability that you actually win. That percentage of the time, you'll win $10,000. So you would multiply that by 10,000. And then so on down the line. 1 time out of 3 million, you'll win $50,000. Right? And 1 out of 3 million, you'll win 200,000. Yes, Sam?
Then do you subtract the loss?
Yep, that's what we'll do in a minute. Yep. So if you do this particular value, what do you get if you type all this into your calculator? Oops. You're probably not something very big.
Can you just say one more time what we're multiplying by?
Sure. So what we're going to do is basically a weighted average. So this gives you a percentage of the time you would expect to win this. Okay. This would give you a percentage of the time that you expect to win this. And there's one other case. there would be a 12,000, or excuse me, a 3 million minus the 12,006, because that's 12,006 cases, over 3 million times 0. Because that percentage of the time we're winning 0, right? Yeah, great.
Alright, we got 0.197.
197-ish? Ish?
I got it as
59 over 300 is about 0.197, isn't it?
59. Yeah, I got 59.
I love how you just like.
It's easier form than one. I got 6 repeating. I got 59 over 300.
Yeah.
They weren't satisfied.
I would. All right, so this is the expected amount that you would win. But is this your expected value? No, because what do you have to pay to win this princely sum of 20 cents? What do you have to pay? 50 cents, right? So your expected value of the game would be the 0.197 minus the 50 cents, which would be about 30 cents negative. So on average, you lose 30 cents for every ticket you buy. This keeps the lottery in.
What about the rest of the tickets? What do you mean about the rest of the subtract those off?
So that was what I was mentioning to Katie. Over here, I would have a 3 million minus the 12,006 over 3 million times 0. That's in the expected value. Yeah, because I don't make anything off of those. All right, so for definition then, for expected value purposes, so let's let x be a random variable. And let's let f of x be the probability mass function of x. Then the expected value of a function g of x is defined as the sum over all x in your sample space of g of x times f of x. We use a capital E. We use a capital E to denote expected value. So what we're doing is a weighted average of this function. So much like the example that we started with, the g of x function here is your winnings. Your f of x is the percentage of time that winnings happen. Okay? So your f of x is the probability. This is the function that you're trying to weight with the probability. So in that previous example, we had the 12,000 over 3 million. The 25 happened that percentage of the time. And so on down the line. So that's how you do expected value of a function. Now there's some very specific functions that we use to be able to analyze random variables. So let's talk though about those really quickly. When you do the expected value of x, this is the sum of x times f of x. This particular one is what we refer to as the mean. The mean of the distribution. Think, if you're a physics person, think of it this way. What you're basically doing is computing the center of gravity. You've got these weights associated by where they are. The f of x is giving you the size of the weights. So the x is the location of the weight. The f of x is the size of the weight. So it's finding the center of mass, center of gravity. That's what the expected value does. In general, again, we're doing a weighted average. We're weighting this value in my sample space by its probability. We want to find out, on average, where should we expect to be. Another one that pops up in calculations, and we'll do a third one in a minute, or probably next time, but we'll need to do the summation of the x squareds. This is referred to as the second moment of x. The expected value, or the mean, is the first moment. Expected value of x squared is the second moment. In general, if you have x to the n, the expected value is the nth moment. So let's see if we can compute a couple of these real quick, and then we'll do a few more on Wednesday. Yes, thank you. Wednesday. Let's look at 2.3-1. This is on page 75. And I want to do part C. It asks for the mean and the variance. I haven't talked about variance yet. I'll do that on Wednesday. But we have f of x is equal to 4 minus x over 6. We want the mean of this distribution. Sometimes we use the Greek letter mu to denote the mean of a distribution. But that just means expected value of x. I'm just telling you that this is just another symbol for expected value of x. I should tell you what the values of x that are possible here. That'd be helpful. Just x is 1, 2, or 3. All right, so according to the formula, we'll do the sum from x equals 1 to 3, because that gets me over the entire sample space. And we'll do x times f of x. Because the formula for doing the mean is just x times f of x. So this, of course, means that we'll plug in 1, then we'll plug in 2, then we'll plug in 3, right? Okay. So I know I need to plug in 1 for x, 2 for x, and 3 for x. So that's why I've got the 1, the 2, and the 3 here. But I also need to plug the x in where? Into the f of x, right? So in the first case, we'll have 4 minus 1 over 6. The second case, we'll have 4 minus 2 over 6. For the third case, we'll have 4 minus 3 over 6. So we'll have a half plus, what is that, 2/3 plus a half. So we get 5/3. So again, notice that this is not one of the possibilities for x, right? 5/3 is not one of the possibilities for x. What this says is that whatever experiment that you're running that gives you that probability distribution function, probability mass function, if you run that experiment over and 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 take the average of your outcomes, you should get 5/3. Expected value is long-term behavior. Right? In short term, you might be really far away from what this value is. By the way, if you wanted to do the second moment, the expected value of x squared, all you would need to do is just square these x values, right? You do 1 squared, 2 squared, 3 squared. You do the same thing. All right, we'll do more of this next time. I posted some review problems for your exam on Moodle with a key. That's on Moodle.
Very much.